Medicinal chemistry HL2. Taxol, a chiral auxiliary case study. Essential idea. Chiral auxiliaries allow the production of individual enantiomers of chiral molecules. Nature of science. Advances in technology. Many of these natural substances can now be produced in laboratories in high enough quantities to satisfy demand. Risks and problems. The demand for certain drugs has exceeded the supply of natural substances needed to synthesize these drugs. Let's review optical isomers. Optical isomers are compounds which are non-superimposable mirror images of each other, like your hands. These molecules must have at least one chiral carbon atom, and the chiral carbon atoms are bonded to 4 different groups. If you remember, pairs of optical isomers are called enantiomers, and the 2 enantiomers are designated as R or S, or D or L, and for amino acids. And the racemic mixture has equal concentrations of the 2 enantiomers. Okay, let's see if you can state whether or not these biological molecules and drugs exist as optical isomers, and mark any chiral compound with an asterisk. Press pause and have a go. Okay, so let's have a look. This one here, this carbon is attached to 4 different things: a hydrogen and NH2 group, COH group, and this big group here. So yes, this is a chiral carbon. So it's an optical isomer. What about here? This carbon is a methyl and a methyl, so no. This carbon has 2 hydrogens, so no. But this carbon here has 1, 2, 3, 4 different groups, so it is a chiral carbon. So ibuprofen is a chiral compound. Over here, nope, there are no chiral carbons, so paracetamol is not. Over here, this carbon here is attached to OH and H, CH2OH, and this big group here. So yes, this carbon here on vitamin C is chiral. So vitamin C is an optical isomer or chiral compound. Over here, penicillin. This carbon here, obviously it'll have a hydrogen too. So this is a chiral carbon. And this one here looks like it's also a chiral carbon. So there's 2 chiral centers for penicillin. Over here, that's no 2 hydrogens, so no. This one, OH, this big group H and H. There, this one's a chiral center. This one is a chiral center. So that one definitely is a optical isomer. Zanamivir. Aspirin, nope. So aspirin does not have any chiral carbons, so it is not an optical isomer. And over here, thiamine isn't either. Good. Okay, physical and chemical properties. Optical isomers, or the enantiomers, have identical physical and chemical properties with 2 important exceptions. Firstly, they have different optical activity, which is a physical property. Different enantiomers rotate plane of polarized light in opposite directions, and these can be detected by a polarimeter. 2. Reactivity with other chiral molecules, chemical, and there's a chemical exception, include biological reactions because most biochemicals in cells are chiral. So, for example, R-thalidomide causes nausea relief and it is sleep-inducing, or relieves nausea and it induces sleep. Thalidomide S is teratogenic. It causes serious limb deformations. So, different enantiomers react with other chiral molecules differently. Another example would limonene. R-limonene is an orange taste or odor, and S-limonene smells of turpentine. From nature to the laboratory, let's look at Taxol, or paclitaxel. It's an interesting example of the challenges faced by researchers in isolating and purifying substances with helpful pharmaceutical activity from natural sources. It's isolated from the bark of the Pacific yew tree, Taxus brevifolia, found in the western US and Canada. One 100-year-old tree gives 12 kilograms tree bark. Removing the tree bark would kill the tree, by the way. 12 kilograms of tree bark gives you 500 milligrams of Taxol, which is only one dose. So it's not the greatest way of getting Taxol. However, Taxol is a powerful and effective anti-cancer drug, particularly against solid tumours in ovarian and breast cancer. So it's a very important drug. That's the structure there. As you can see, it's quite large, and there are absolutely loads of chiral centres. Press pause and see if you can find how many there are. Oh, it says just underneath. There are 11 chiral centres. That makes the synthesis of Taxol from small precursors very difficult and expensive. Why don't you find the 11 chiral centres? Press pause, have a go. Okay. There you go. There are all the chiral centres marked with an asterisk. I'll go back on there so you can have a bit of a longer look. Alright. So, how does it work? Well, the mechanism of action is the Taxol binds to the microtubules that form during mitosis and prevent them from breaking down. This stops cell division and prevents the growth of the tumour. Extraction of Taxol from the specific U tree. In spite of the high effectiveness of Taxol, there are several significant difficulties in relying on the specific U tree as a source of the drug. Obviously, it's a very, very low yield. The bark is only 0.0004% Taxol. Removing the bark kills the tree. And trees are very slow growing. It takes 200 years to reach maturity. They are located in a very sensitive ecosystem as the home to the spotted owl. Difficulties in the synthesis of Taxol from small precursors. Over 30 steps are required to synthesize Taxol from small precursors. With 11 chiral centers, there are very large numbers of enantiomers of Taxol, and each enantiomer has its own unique biological property. Only one enantiomer has the desired therapeutic activity. Isolating the powerful anti-cancer enantiomer is possible, but it is time-consuming, costly, and wasteful. The European U Taxus bracata. I think that's how you say it. The leaves of the European U tree, the leaves of the European U contain 10-deacetylbaccatin, which is a precursor to Taxol. The yield of the precursor is 0.2%, which is 50 times greater than that of Taxol. And only a few steps are required to convert 10-DAB to Taxol. And you can see 10-DAB at the bottom there on the left and Taxol on the right. I guess they are very similar. You can see kind of this bit and this bit. Are they identical? Maybe they are identical. No, they're not. So it's a bit different. But they are very similar, obviously, apart from this bit and that bit. Okie dokes. Obviously, harvesting leaves is not as damaging as removing bark from a tree. Okay. Semi-synthetic production of Taxol. Asymmetric synthesis, enantiomeric selective synthesis. This is a special process by which the laboratory synthesis of an optically active compound will only produce one enantiomer. A chiral auxiliary molecule is used in this method. A chiral molecule has a particular shape, and a chiral auxiliary molecule can be removed after the synthesis reaction and reused. The 3D shape of the chiral auxiliary molecule prevents the formation of one of the enantiomers, and it attaches near a reactive site on a reactant. So let's have a look in more detail at some asymmetric synthesis or enantiomeric selective synthesis. Propanoic acid to give 2-aminopropanoic acid. We have propanoic acid in the chiral steps. We could get a racemic mixture of 1:1 of the enantiomers here of 2-aminopropanoic acid. Okay, you can see here is the chiral center. Here, okay. But if you stick an auxiliary on, so you're replacing the this group here with a large auxiliary molecule which has a unique 3D shape, then you do the chemical steps to attach the NH2. This here blocks the formation of one enantiomer due to steric hindrance, and then you can remove it and it can be reused in other syntheses. And so you're taking the auxiliary off and you're left with only one enantiomer produced as a major product. Very clever. Another example would be synthesis of 2-hydroxypropanoic acid. The normal steps would give would make this a chiral center, and so we'd get a mixture of both the R and the S. But once again, we can put the chiral auxiliary added here, which blocks the formation of one of the enantiomers. You can form the enantiomer that you want here, and the chiral auxiliary can then be removed, and you end up with only the desired enantiomer formed. Wonderful. So, the difficulties and the new directions. Small quantities of other enantiomers may be produced, which is a difficulty. And additional steps required to purify the desired therapeutic enantiomer. 13 steps are required to convert 10-DAB into Taxol, which gives a lower yield. And many solvents and organic reagents are used, which can have a negative environmental impact. Some fungi have been found to produce Taxol, and plant cell cultures may be used to synthesize Taxol. Assessing product purity by polarimetry. The purity of an optically active substance may be determined using a polarimeter. You can review organic chemistry to find out how these things work. A pure substance of one enantiomer, 100% concentration or 100% purity, will rotate plane polarized light in one direction at a defined angle. If the concentration of the enantiomer changes, the angle of rotation will change. The purity of a preparation of a desired enantiomer can be determined by measuring its angle of rotation and using a calibration curve. Question: if a sample has an angle of rotation of 140 degrees, what is the percentage purity of the sample on this graph over here? Well, the optical purity would be, you go to the angle of rotation 140, it's there, so it's just under 80%. And that is the end of this presentation. Splendid.